All right, so just to review what we had been doing, we're just doing an example here. Following table shows the relationship between grade and having a driver's license at a high school. So here's the information, and we filled in these totals over here. Notice the total is 1 for 100%. All of these decimals would represent percentages. So in other words, 27% of the people, the students in this school are freshmen, 23% are seniors, and 67% have no license, and 33% do have a license. So we found a few probabilities so far, so now we're going to work on finding a couple more probabilities. Probability number 5, what is the probability that they are a legal driver is a senior? Probability that a legal driver is a senior. Okay, so a legal driver would mean they have their license. Okay, so a legal driver means they have their license. So we know that. This is the given. And we want to know the probability that they're a senior. So this translates into a conditional probability. This is the hardest thing you have to do. On number 4, it was the find the probability that a senior has a license. So this is the part you're given, you're not given. This is the part that you want to find the probability of, but you know this is the given part right here. You know they're a senior. So the probability that they have a license, given that you already know that they're a senior. What this does in your two-way table is it narrows you down to a row or column for the bottom number. So in this case, the fact that we knew that they were a senior narrowed it down to the fact that we were only dealing with 23% of the population. And then of those that had a license were 0.16, so we divided those to get the probability. So now down here we're doing something very similar. So this is the given part, that they have a license. So the probability that they have a license is given. We want to know what's the probability that they're a senior. So it's like the backwards of this problem, not the same thing. So now, knowing that they have a license, if we go up here, narrows us down to that row right here. So we're only dealing with 33% of the people have their license. Of those, how many are seniors? That would be 0.16. Notice how it's the same top number because we're, same top number, but the bottom number differs because of what we know. The given information narrows us down. Here it gave us this column that we're dealing with, so that would be our bottom number. Here we know they have a license, so now we have the bottom number being 0.33. So now we take 0.16 divided by 0.33, and we get that the probability would be 0.4848. All right, so that's just an example, kind of reviewing the same type of thing from the Titanic example in the last video. Now we're going to jump back to the notes, and we're going to talk about something called independence. So independence now, we can also formally define independence. Events A and B are independent whenever the probability of event B happening, given that event A has happened, is the same as the probability that event B has happened, given that A complement has happened. All right, is the same as just the probability of B. So in other words, if they're independent, all these probabilities are the same. Now, when we talked about independence before, we talked about making a segmented bar chart. And basically what we were looking in the segments were probabilities, percentages. And if they looked the same, hence the equal, then we could say that they were independent, because you can't tell what's happening based on saying if it's male or if they died. So in other words, that is knowing the outcome of event A. This is the definition of being independent. Knowing the outcome of event A does not change the probability of event B. So whenever you are asked about independence, this is the definition you should use to justify your answer. And I plan on showing you in this video exactly how to do that. So we can really see that the original multiplication formula is just a special case of the general formula, because the probability of A times the probability of B, given that A has happened, simplifies to just the probability of A times the probability of B when they are independent, So using the examples from yesterday. So we want to know, first of all, were being a male, probability of being a male, probability of surviving, were they independent on the Titanic? And then, well, we'll talk about disjoint first. So disjoint means you cannot be both at the same time. Okay, that's what to be disjoint, it means you're not both at the same time. So I go over here, can I be a male who survived? Yes. So these are not. Can I be both at the same time? The answer is no. Sorry, it's not no. The answer to that is yes. I can be a male who survived. So that means that they are not not disjoint. Okay, they're not disjoint because I can be both at the same time. So we've already answered that question. Now we want to see if they are independent. So we have to look at the probabilities that we had from before. So those probabilities, let's see, we want to show independence. So we are going to have to look up here. So we've got two events. We've got male and we've got surviving. So the probability, let's see, this says of B given that event A has happened. So we're just going to pick an event for event B, and we're going to let that be male. So we're going to find the probability of being male given that you survived, and then we're going to compare it to the probability of just event B, which event B would be the first one here, if you notice. Event B would be the one we were trying to. So if we just found it by itself, okay, the probability of just that one event, and the probability that they're a male given they survived. If those two are equal, that's really what this is saying up here. I'm actually just choosing two parts of it, because if I can just show two parts are not the same, then I can show that they're not independent. So otherwise, if these two are the same, then I have to check the third thing up here. So the probability that they were a male, given that they survived from the notes before, was 367 over 711, which if I divide that, that would be 0.5162. Okay, so that's the probability of being a male given that you survived. Now, what's just the probability of being a male? Well, the probability of just being a male was 1,731 over 2,201. So, and that is actually 0.7864. So are those two equal? No, it's kind of a question mark. If you're asking the question if they're equal. You find these probabilities. These are not equal, so they are, being a male and surviving are not independent. Okay. All right, so now this is the example that we just did. We're being a senior and having a driver's license independent. Okay. So now I'm going to go to my example here. I want to know if being a senior and having a driver's license are independent. So this is basically what we were dealing with. So hopefully you wrote that all down. So being a senior, so I'm going to let that be my first event if I go up here. So the probability of being a senior, given that they had a driver's license, so that would be the given. And we want to see, question mark, is it the same as just the probability of the first event, okay, the event. So if I was just finding the probability of having a driver, of being a senior, okay, finding the probability of being a senior, knowing that I had a license, if those are equal, then it's independent. Okay, if those are the same probability, then it's independent. All right, so the probability of being a senior, given that I had a license, that we did in number 5 in the last little bit of notes, and that was 0.4848. And just the probability of being a senior, the probability of just being a senior was 0.23. So these are not equal. So being a senior and having a driver's license, having a license, are not independent. So now the next question is, are they disjoint? Can I be a senior and have a driver's license? The answer is yes. So these are not disjoint. All right. So now note, if events E and F are independent and the data we have is from a random sample, then the probability of E, given that event F has happened, is approximately the same as event E. None of these were approximately the same as each other. If they're off by a few decimals, that's okay, but typically you want those the tenths decimals to match up in order to say they're independent. So in other words, the probabilities may not be exactly the same because of sampling variability. How close do they need to be? Well, that's where we'll wait until Chapter 6. How close do they need to be? What kind of range are you going to allow? I just said that at least the first digits have to be the same. But would I allow like 0.48 to be the same as 0.40? Are those close enough? That's the type of thing we need to figure out. That won't be till the very end of the year that we'll learn a test actually called the chi-squared test that, it's written chi-squared, I like to make that symbol, to decide if they're close enough. So now we're going to move on, and this I'm probably actually going to need to go to a third video on this. So this is important that you know how to do these next things, and we're going to basically be making something called a tree diagram. All right, so suppose that in a certain company, 5% of the employees use drugs. The company decides to test all of its employees for drugs with a test that is 95% successful. In other words, it correctly identifies 95% of users as users and 95% of non-users as non-users. So let D be the event that the employee uses drugs, and P be the event that a person tests positive. So the probability, these are our events, we're going to use D and P. Okay, so the probability of event D, the probability that the employee uses drugs is only 0.05, and the probability that they test positive is 0.95. Okay, so those are the events that we know the probabilities of. So now let's look at the probability of D complement would mean not using drugs, so that probability would be 0.95. And the probability of P complement, which would mean testing negative, okay, so this means test positive, and this one over here means test negative, and that probability is 0.05. This probability of D means they use drugs, and this probability is no drugs. Okay, but to simplify things, instead of having to write the words, we're going to use P and D complement and P complement. So we want to express this in a tree diagram. So a tree diagram, we basically start with the type of employees the company has. You just have to start somewhere where there's just two groups. There could be three groups, like you could have different groups of political parties. So the first thing, I'm going to split this into drug users and not drug users. So the probability that they're a drug user is 0.05. So the probability of being a drug user is 0.05. The probability of not being a drug user is 0.95. Now, we're going to give tests to each of these people. We're going to give a test to everybody. And the results of the tests of drug users can have one of two answers. It can be that the probability that they test positive, okay, would be 95%, because they are drug users. 95% of them are going to test positive. But the probability that they test negative, P complement, is actually 0.05, because even though they are drug users, our test is only so accurate. All right, so now the probability that they are not drug users is 0.95. They're all going to get a drug test too. The probability that they test positive is only 0.05. It's going to tell the truth 95% of the time and lie 5%. So even these people who don't use drugs are going to get, 5% of them are going to get test positive, and P complement, 95% of them are not. So on the next video, I'll finish up this tree diagram and finish up the notes for day 33.